This is the second part of the Dynamics MCQs, looking at question 16. It says that a roller coaster car is raised to a height of 65 meters and released from rest. What is the maximum possible speed of the car? So that can only happen if all the gravitational potential energy is transferred to kinetic energy. In other words, we're going to assume no friction and no air resistance. So there is no transfer of energy through work done against friction. So the gravitational potential energy, which is mgh, that's going to be 65 times the mass of the car times 9.81, which gives me 637.65 times the mass of the car. The kinetic energy is equal to half mv squared, and if that is maximum, it means that all gravitational potential energy has been transferred to kinetic energy, so that would be equal to 637.65 times the mass. So the masses cancel, which gives me v squared is equal to 2 times 37.65. So v is equal to the square root of that. So 637.65 times 2, and then take the square root of that, which gives me an answer of 35.7 meters seconds. So for question 16, the answer is C. Question 17, again, is one of the questions to do with looking at expressions, and impulse is force times time. So force times time, that's Newton's seconds. Here we've got Newton's seconds to the minus 1, so it can't be this one. We also know that force times time is equal to the change in momentum. Momentum is measured in kilograms, meters second to the minus 1, so this one. Yes, it could be this one. It can't be this one because I've got seconds to the minus 2. And here I've got seconds newtons to the minus 1. So that would be T over F. This one would be F over T. So that was not possible. So the answer is 17, for 17 is B. Question 18, what is represented by the area under a force displacement graph? So we're saying we have force on the y-axis, displacement on the x-axis, say in meters, with some sort of function, and we're looking for what does this represent the area under that curve. Let's imagine that we have a case where the force is constant. Here again we have displacement, we have force in newtons, and we've got some constant force, and the distance travelled is s. Then what is this area? The area is equal to, well, from there to there, that's force on that side, and this times is s, so that gives me the area is force times displacement. And we know that that is work done. It's the definition of work done. So in the case where the force is changing, once again, the area under the force displacement graph is work done. So it's answer C. Okay, question 19. A ball of mass 0.2 kilograms is thrown and moves in a curved path. At Q, it's traveling horizontally. Okay. Assume air resistance is negligible. What is the momentum of the ball at Q? So this is a projectile, and we're traveling in a parabolic path, and we have acceleration due to gravity. minus 9.81 meters per second squared. So I'm assuming that the upwards direction is the positive direction. So initially the speed of the ball is 20 meters per second. It's thrown at an angle of 60 degrees. So this velocity could be broken down into its horizontal and vertical components like that. So here's my horizontal speed. So that gives me that the horizontal velocity is 20 cos 60. Now, as with all projectiles, the acceleration is only vertical. There is no force in the horizontal direction. So the horizontal velocity of the ball is not going to change. It's going to remain what it was at the start. So that gives me the velocity of the ball traveling horizontally, 20 times the cos 60, which gives me 10 meters per second. And we're looking for momentum. So momentum is equal to mass times velocity. So that gives me that the momentum is equal to 0.2 multiplied by 10, which gives me the momentum is 2 kilograms meters seconds to minus 1. So the answer is 2. And we can notice that the units they're using there are Newton seconds. So we have force equals mass times acceleration. That is 1 Newton is equal to 1 kilogram meters seconds minus 2. So that means that I can take one of my seconds across to the other side. 1 Newton second is equal to 1 kilogram meters seconds to minus 1. Which of course is another way of restating our force times time is equal to the change in momentum. So our answer is B, 2 Newton seconds. So question 20, we've been shown a graph of force against time, and we're asked to work out the momentum gained from time 0 to time t equals 10 seconds. We know that the change in momentum is equal to force times time. So more generally, the change in momentum is the area under the force time graph. So we're looking at the area under this graph between time t equals 0 and 10 seconds. So we're going to work these out separately. So I've got the area of this bit. So I've got the area is equal to 4 newtons times 4 seconds. That's 16 Newton seconds there. And then I've got the area of this trapezium. So the area is equal to half sum of the parallel sides. So that's 4 and 10 multiplied by this distance between them is 1. That's 2, 4, 6. So that area is equal to 42 Newton seconds. So the total area is equal to 16 plus 42 Newton seconds. So that equals to 58 Newton seconds. But that's also equal to change in momentum. So the change in momentum is answer D, 58 kilograms meters seconds to minus 1. Okay, question 21. We have a railway truck of mass 8,000 kilograms. It's traveling along with a velocity of 2.5 meters per second. It collides with a stationary truck which has a mass of 12,000 kilograms. The two trucks move together at the same velocity after the collision. When they say that they move together afterwards, this means we have an inelastic collision. So momentum will be conserved, kinetic energy is not conserved. Okay, so what is the change in momentum of the 8,000 kilogram truck due to the impact? So we're going to use the fact that there's a conservation of momentum. So before, the momentum before is equal to 8,000 multiplied by 2.5. So that's equal to 20,000 kilograms meter seconds minus 1. After the momentum afterwards is equal to, well, they're joined together, so now you have a total mass of 20,000 times the velocity after the collision. So we can say that because the momentum before equals the momentum afterwards, which is 20,000 times the velocity, is equal to 20,000 kilograms meter seconds minus 1, which is the momentum before. Therefore, the velocity is 1 meter per second. So to say what is the change in momentum, that means for the 8,000 kilogram truck only, the momentum before again was 20,000 kilograms meter seconds minus 1. The momentum afterwards is 8,000 multiplied by 1, so it's 8,000 kilograms meter seconds minus 1. Therefore, the change in momentum is 20,000 minus 8,000, which is 12,000 kilograms meters seconds minus 1. And remember, these units are the same as Newton seconds from impulse, so that means the answer we have is answer B. Okay, question 21. Body X moving with the velocity V. So we have, once again, with body X moving with velocity V, collides elastically, and this is important, as we'll see later, with a stationary body Y of equal mass. So we have velocity before, for X is V, the velocity for Y is 0. So that means that the total momentum before is m times v, and which is in this direction. And then we're looking at what the velocities are after the collision. So we know that the total momentum afterwards also has to be m times v. So we need to think about what this means in terms of what possible answers we could have. Okay, so for A, what we've got is it's suggesting that both of the objects have a velocity of v over 2. This means that, well, in terms of the momentum afterwards, that would be saying that X has a momentum of m times v over 2 plus Y with m times v over 2 to give us mv, so that's correct, momentum is conserved. But in this case, the objects would be stuck together, so this would be an inelastic collision. And we'll see in a moment, in a bit more detail, why that's the case. In this case, what we have is it's suggesting that Y is going to move away at half the original velocity of X, and X is going to recoil or bounce back in the opposite direction. Well, what does this mean? This means that the momentum afterwards is going to be minus m times v over 2 plus m times v over 2, which gives me 0. So this cannot be true because it would mean momentum is not conserved. This last one, this is part C, the third one. It says here that X bounces back with a velocity of minus v. So we've got the total momentum afterwards is minus m times v plus 0. It gives me minus mv. Magnitude is the same as what we expect. However, this would be suggesting that the direction is changing, which would mean that momentum is not being conserved because the direction is changing. So this one is not true. So this leaves us with the last one. We can check that. We're saying that we've got the momentum afterwards is mass of 1 of X body X times 0 plus the mass body Y times V, which equals m times v. Yeah, that works. So this is our answer. Now I said that we knew that it wasn't A because in A this is saying that the two objects are stuck together, so it's an inelastic collision. But let's look at this in a little bit more detail to see why this is the case. Remember that in elastic collision kinetic energy is conserved. In inelastic kinetic energy is not conserved. Be careful, that means that what they're saying when they say there is an inelastic collision, they're saying that some of the energy is transferred into some other form. So it could be that it's transferred into the work done against the friction, where the two objects come together and they're either damaged and there's heat generated. So some of the energy is converted into thermal energy, which would mean that kinetic energy is not conserved. So let's see in this case, in case A, what it means when these are both stuck together with this velocity. Now, remember, momentum is being conserved here, so these look correct. It's on the face of it, this is a valid answer. So let's just look at this in terms of kinetic energy. So before, the kinetic energy before was equal to half times the mass of x, which was m, times the velocity x, which is v squared, and there's no kinetic energy related to body y. So afterwards, now my kinetic energy is equal to, just make a dash on there to show the kinetic energy afterwards. So for x, I've got a half times m times v over 2 squared, and for y, I've got a half times m times v over 2 squared. So that would give me that the kinetic energy afterwards, well, it's going to be a half v squared, which is fine, but here this is a quarter and that's a quarter, so that's times a half overall. So my kinetic energy is only a quarter mv squared instead of being a half mv squared. So kinetic energy is not conserved. So this is an inelastic collision, which is not what they said in the question. So this one is definitely wrong. The answer is D. Okay, so this next question, it says that we've got an electric motor of input power 100 watts, raises a mass of 10 kilograms vertically at a steady speed of 0.5 meters per second. What is the efficiency of the system? So we're saying that the power in is 100 watts and this is, that's electrical power in, and then we're going to have a certain number of watts out, which is our to raise the object. And then we've got a certain amount of power that's wasted, and this would be probably wasted through thermal energy as work done against friction. Okay, so how can we work out how much of the power is transferred to do actual useful work? Well, we can see what this means in terms of the force needed to raise this object. So remember, work done is equal to force times distance. Power is equal to work done over time, so that gives us power is equal to force times distance divided by time, or in other words, power is equal to force times speed. So in this case, what is the force? Well, the force is due to weight, so that's equal to m times g. So that gives me that the force is equal to 10 times 9.81. Gives me a force equal to 98.1 newtons. The velocity is 0.5, so therefore the power is equal to 98.1 times 0.5, so that's 49.1 watts. And then we're looking for the efficiency. Well, the efficiency is equal to the useful power divided by the total input times 100 to change it into a percentage. So that gives me, that would be equal to 49.1 divided by 100 times 100. So 49.1%, answer C. Okay, question 24, it says, a firework is fired vertically up into the air and subsequently falls to the ground. Which quantity relating to the motion of the rocket is never zero before it hits the ground? Assume that the air resistance is negligible. Well, if we think about what happens, we throw the object up. So if I was to show something like this, which shows displacement and time, so vertical displacement with time. So the vertical displacement increases, reaches a maximum, and then comes back down and hits the ground again. What we can say is that here we have high speed upwards. Here, velocity is 0. Once it reaches the top, and then it starts to fall back down again. So again, it's got a high velocity just before it hits the ground. So when we look at these quantities, the first one we can say is acceleration. Well, what is it that's causing acceleration? Acceleration is caused by a force. We can assume here that the firework, there's only a force upwards once it's launched. So the only force remaining after it starts moving through the air is the force due to gravity. So that's going to be constant, therefore the acceleration is constant. So this could be our answer, constant at 9.181 meters per second squared. Velocity, we can see from my little discussion of this graph, sketch of a graph that I've drawn here, that this cannot be the answer because it does reach 0 up here. And obviously if the velocity can reach 0, that means that the momentum can be 0. And then finally, we've got lots of kinetic energy here, but some or most of that kinetic energy is transferred to gravitational potential energy, which then is transferred back into kinetic energy as it hits the ground. So that all means that the answer for 24 has to be A, acceleration. Right, question 25. It says two bodies of different masses undergo an elastic collision in the absence of any external force. Which row gives the effect on the total kinetic energy of the masses and the magnitudes of the forces exerted on the masses during the collision? So we really have to decide, is kinetic energy conserved in this case? And then in terms of the magnitude of the forces, does the fact that they have different masses, does that actually mean anything? Will that have any effect? So when we look at this, we can say that, well, we know that kinetic energy has to be conserved. Why? Because they've told us it's an elastic collision. So the answer is not going to be C or D. We can immediately rule those two out. So we're left deciding on the magnitude of the forces. Should the forces on each object be the same, or is the force greater on the smaller mass? So to think about this, I'm just thinking about, again, a diagram, and what's happening is, let's say the two objects are acting like this. So an object is coming this way, another object is coming that way. So when they collide, what happens is that there is a force on object B this way. So this is the force on B due to A. So in other words, we can say object A pushes object B. And as we've seen looking at Newton's third law, whenever there is a force of one object on another object, there is always an equal and opposite reaction force, but only when there are two objects. So we've got object A pushes object B, therefore object B pushes object A with equal and opposite force. So So there's a force on B due to A, which means that there's a force on A due to B. And those forces are equal, which means that our answer to this question has to be A. Okay, so question 26. Acceleration due to gravity, we're taking this as 10 in this case, and it tells us that the acceleration due to gravity on the moon is a sixth. So an object has a weight of 5 newtons on the Earth is dropped from rest above the moon's surface. What is its momentum after falling for 3 seconds? Okay, so we could work out the speed and then work out the mass and calculate the momentum from that. But we can take a quick shortcut on this, which is that we know for a start that the force or the weight on the moon is equal to a sixth the weight on the Earth. Therefore, the force in this case is going to be 5/6 newtons. So that gives me the force is equal to 0.83 newtons. Okay, and we're told that it falls for 3 seconds. We're looking for the momentum. So in this case, we can use the impulse equation. The momentum at the start is 0, so the change in momentum is going to be equal to its momentum after 3 seconds. So that gives us the change in momentum is equal to the force, which is 0.83, multiplied by 3. So that gives me an answer of 2.5 Newton seconds. So the answer is going to be A, and we note again that Newton seconds are the same units as kilograms. Newton seconds are the same units as kilograms meters per second. Right, so now question 27. We have a golf club strikes a stationary golf ball of this mass, and the ball leaves a club with this amount of speed. They tell us that the average force is 7,800 newtons. How long are the ball and club in contact? So we can use our equation for the impulse, which gives us the time is equal to the change in momentum over the force applied. Okay, so the time is equal to, we have 4.8 times 10 to the minus 2 multiplied by 95, all divided by 7,800. So that gives me a time of 5.8 by 10 to the minus 4 seconds. Okay, so it's saying for around about a half a millisecond is the time the club is in contact with the ball. We wouldn't expect either of these answers, because that would be suggesting that the club spends a long time in contact with the ball, which you can imagine wouldn't be the case. But it's answer A is obviously what we're able to calculate. Okay, question 28. A car's engine produces a useful output power of, so this is the useful power of 6.5 by 10 to the 4 watts. We know that the mass is 950 kilograms, and we're told the slope is at 12 degrees to the horizontal, and we're told also that we can ignore the resistive forces. Right, so what I do here in this case is I just do a little diagram. So I know that the only force acting on this object is the weight. It's moving up at a constant speed. So we're interested to see the work done against the force, which is the force downwards. So what is the steady speed of the car? Well, we need to know the force in this direction. So what we have is that we have the weight can be divided into force along the slope and the force perpendicular to the slope. So that gives me the force along the slope is equal to the weight times the sine of 12. So the force is equal to 950 times 9.81 times the sine of 12. That'll give me a value of force is equal to 1937.6 newtons. Right, now the car engine, in order for the object to travel at a constant speed, so we've got the force down due to gravity, and then we have the output of the car, and these have to be equal, so the car's force output is also 1937.6. So overall, no resultant force. Forces are balanced. So, and now we can use the fact that power is equal to force times velocity. It gives velocity is equal to the power that's produced by the engine divided by the force being produced, which gives us an answer of the velocity is 33.5 meters per second. So answer C, 34. Okay, question 29. A body falls freely with negligible air resistance. What quantity of the body is its rate of change of momentum? So rate of change of momentum, that's going to be the change in momentum over the change in time. So what's that going to be equal to? Well, we know that force times time is equal to the change in momentum. So that's going to be equal to the force on the body. We're told there's negligible air resistance, so the only force on the body is the force due to gravity. Clearly not mass, power, or kinetic energy. Those aren't force values. So the answer in this case is very simple. It's weight. The mass of P is 10 times greater than the mass of Q. So what they're saying here is that both of these, we have the momentum of P is equal to the momentum of Q, because both of them had the same amount of force applied for the same time. However, mass of P is 10 times the mass of Q. So if I substitute in for MP, that gives me that the velocity of P is 1/10 the velocity of Q. Right, now in terms of kinetic energy, what does that mean? Well, the kinetic energy for P is equal to 1/2 times the mass of P times the velocity of P squared. So that equals to 1/2 times 10 times the mass of Q times 1/10 the velocity of Q, but all squared. That equals to 1/2 mq vq squared times 10 times 1/100. Now obviously this is the kinetic energy of Q, therefore the answer is A, 0.1. Right, question 31. A bullet of mass 10 grams is fired with a velocity of 100 meters per second from a stationary rifle of mass 4 kilograms. Consider the rifle and the bullet to be an isolated system. So this is saying isolated system, I mean no external force, so momentum is conserved. That's what they mean by that. What are the recoil velocity of the rifle and the total momentum of the rifle and the bullet just after firing? Well, if we look about the momentum beforehand is they're stationary, so it's 0. Right, so that means since momentum is conserved, it means whatever we've got, the momentum afterwards also has to be 0. Therefore, B and D are definitely wrong, so we can immediately eliminate those as possible answers. So now we need to think about what might the recoil rifle velocity of the rifle be. Well, we can say that the momentum of the bullet, or the mass of the bullet, is equal to 10 grams. So that's equal to 1 by 10 to the minus 2 kilograms. And the velocity is 100 meters per second. So the momentum of the bullet is equal to 10 to the minus 2 times 10 to the 2 equals to 1 kilogram meter second. That's 1. Now, this has to be 0. Therefore, the momentum of the rifle has to be minus 1 meter seconds minus 1 in order for the overall momentum to be 0. So the velocity of the rifle is minus 1 divided by the mass of the rifle, which is 4. So it gives us the velocity of the rifle is equal to minus 0.25 meters seconds minus 1. So the answer is A. Okay, this is an interesting question, question 32. The mass of fuel in a racing car decreases during the race. As a result, the lap time decreases. Which of the following could explain the decrease? Number one, there is less friction on the racetrack. Well, the racetrack hasn't changed. We can assume that there's no change in the weather or something like that would cause a change in the surface of the racetrack. There may be some change in the level of friction because of a change in mass in the car, but we can assume that this is negligible. So we're going to say that it's not due to the racetrack. Just jump down to the bottom. The engine is more efficient. There's no reason for the engine to have changed its efficiency. So we're going to say that that won't be any different. And then we have the maximum speed of the car has increased. The maximum acceleration and deceleration are greater. The maximum speed of the car is essentially the terminal velocity of the car, which happens when there is a balance between the resistive forces and the friction and air resistance against the forward force from the engine. So again, this is going to have minimal effect, the change in the mass of the fuel on this car, on the terminal velocity, which is primarily going to be determined by the mass of the car itself and more particularly the aerodynamics of the car. So I'm going to say that I believe this won't change. However, what will change is from force equals mass times acceleration. It means that the acceleration is greater for the same amount of force when the mass is decreased. So the answer here will be C. Right, question 33. We have a deep space probe traveling forward at a constant speed is briefly acted on by a force at right angles to the motion. What is the effect of this force on the forward speed and sideward speed of the probe? So what we're saying is we have the probe, it's traveling in this direction, it's moving at a constant speed, and we apply a force at exactly right angles. Well, this force, there will be no resultant force in the direction that the object is moving or in the opposite direction. So this will have, there is no acceleration in the direction it's moving. So we would expect its forward speed to be unchanged. Its sideward speed, the speed it changes to the side, will definitely be changed, and in this case will increase. So can't be this one because it says the sideward speed is unchanged. It has to be either A, B, or C. but there's only one that says the forward speed is unchanged, so the answer is C. Question 34, which of the following statements is correct? The force acting on an object is equivalent to, well, it can't be change in momentum because change in momentum is force times time. It could be impulse per second, because that's saying that we're looking at impulse, which is force times time, per second, so divided by time, so that equals force. The energy it gains per second, well, energy is equal to force times distance, not force times time. And acceleration per meter, well, energy is equal to acceleration times seconds. That's not correct, so it's not going to be equal to that. Force is equal to mass times acceleration, not acceleration per meter. So the answer is B. And then finally we have, immediately after takeoff from the surface of the Earth, a rocket of mass 12,000 kilograms accelerates upwards at this amount of acceleration. What's the thrust produced by the rocket? So we have a little diagram that says we have our rocket with its mass. It's going upwards, but in the free body diagram we need to show all the forces. So the force down is the weight. We can find the overall resultant force is therefore thrust minus the weight. So the thrust is equal to the force plus the resultant force plus the weight. The resultant force is also equal to mass times acceleration. So we have the force is equal to 12,000 times 1.4, which gives me the resultant force is equal to 16,800 newtons. Weight is equal to mass times acceleration due to gravity, so weight is equal to 12,000 kilograms multiplied by 9.81. Gives us an answer of weight is equal to 117,720 newtons. Therefore, the thrust is equal to 16,800 plus 117,720, which equals 134,520 newtons. So answer C. Okay, so that concludes the second part of the multiple choice questions